Hello there, and welcome to the Calm Science Sleep channel. I'm Jeffrey, and so glad you found your way here. Maybe the day was long, or maybe you're simply the kind of person who likes to fall asleep thinking about the most mysterious places in the universe. Places so strange and so distant that the mind can barely hold them. Either way, tonight's journey is for you. There's nothing you need to do now. Just let your body settle, your breath slow, and your thoughts grow soft at the edges. Because tonight, we're drifting somewhere very few have dared to imagine in full. We're going inside a black hole, not in the way of danger or fear, but in the quiet, curious way of a dreamer who wants to understand what the universe has hidden at its most extreme depths. We'll travel gently, one idea at a time, from the surface of dying stars to the very edge of the known universe, through warped time and shredded light, and the strange mathematics that describe places no telescope can ever show us. Some of what you hear tonight may stretch your sense of what's possible. Other parts may simply drift past like music, soothing in its strangeness, quietly beautiful, even when the ideas are vast. And just before we begin, if these slow and thoughtful explorations help you rest, or if they give you a gentle way to end your day, consider liking and subscribing to the channel. It helps others find their way here, too, one sleepy soul at a time. Now, if you're ready, let's begin. A black hole begins where a star ends. That might seem like a strange place to start, but to understand what lies inside a black hole, you first need to understand how one is born. And it begins, as so many things in this universe do, with a star. Stars are not permanent. They burn for millions or billions of years depending on their size, fusing hydrogen into helium deep in their cores, releasing light and heat and pressure that hold them upright against the tremendous pull of their own gravity. It's a kind of balance, a delicate, ongoing negotiation between the outward pressure of nuclear fire and the inward pull of gravity. While there is fuel, the star stands. While the fire burns, nothing collapses, but the fuel runs out. And for the most massive stars, the ones many times heavier than our sun, what comes next is almost unimaginably violent. When a massive star exhausts its fuel, the balance fails. The core, no longer supported by the pressure of nuclear fusion, collapses inward in a fraction of a second, not slowly, not gently. In the time it takes to blink, the core of a star more massive than anything on Earth shrinks from something the size of a city into something smaller than a grain of sand. The collapse is so sudden, so complete, that the outer layers of the star rebound off the core in a catastrophic explosion. We call it a supernova. For a brief moment, that explosion outshines an entire galaxy. Every star in the Milky Way, all 100 billion of them added together, and a supernova can still outshine them all. But what's left behind after the explosion is what we're really here to talk about. In the heart of that spent star, something remains, something so dense, so compressed, that even light cannot escape from it. A black hole has been born. The first person to seriously describe such an object was not a scientist with a telescope, but a man doing mathematics in a trench during the First World War. His name was Karl Schwarzschild. In 1915, while serving on the Russian front, Schwarzschild received a copy of Einstein's newly published general theory of relativity. he read it in the field, surrounded by the chaos of war, and within weeks he had solved Einstein's equations exactly. What he found was a description of spacetime around a perfectly spherical mass, an object with no rotation, no charge. But buried in his solution was something strange, a boundary, a point of no return. If matter were compressed beyond a certain radius, the mathematics suggested that space-time itself would curl inward so completely that escape would become impossible, even for light. Einstein himself thought the result was a mathematical curiosity with no physical meaning. He didn't believe such objects could really exist. He was wrong. Schwarzschild died months later from an illness contracted at the front. He never lived to see his equations confirmed, but the boundary he described now bears his name. We call it the Schwarzschild radius, and it defines the edge of a black hole, the surface of no return, the event horizon. Let's drift there now. The event horizon. Picture yourself in a spacecraft approaching a black hole from a safe distance. From far away, the black hole is invisible. It produces no light, but the space around it tells a different story. Stars behind it are bent. Their light curves around the black hole's gravity in sweeping arcs. You might see the same star twice, or even more, as light takes different paths around the enormous gravitational well. If the alignment is perfect, a star directly behind the black hole appears as a ring of light, a glowing halo, an Einstein ring, perfectly circular, impossibly bright. The black hole itself is a silhouette, a darkness against the glow. And at its edge, the event horizon shimmers, not because the horizon itself glows, but because infalling material, gas and dust, and torn matter heats to millions of degrees as it spirals inward. It forms an accretion disk, a swirling, blazing ring of doomed material falling endlessly toward the center. In 2019, an image of exactly this was captured. A team of scientists coordinated radio telescopes across the entire planet, turning Earth itself into a single giant lens. They pointed it at the center of a galaxy called M87, 53 million light-years away. And what came back was history. A blurry, orange, glowing ring with a dark center. The shadow of a black hole. The first direct image of one. Not imagined, not simulated. Real. That dark center is the event horizon, the surface beyond which nothing returns. Now imagine you're moving closer. Your spacecraft drifts slowly toward that boundary. From the outside, anyone watching you would notice something extraordinary. You would appear to slow down, not because your engines had failed, but because of time. Near a black hole, gravity bends not just space, but time. The closer you are to a massive object, the slower time runs for you relative to someone farther away. This isn't a metaphor. It isn't a thought experiment. It has been measured right here on Earth, with atomic clocks, with GPS satellites, with careful experiments done over decades. Time genuinely ticks more slowly in stronger gravitational fields. Near a black hole, this effect becomes dramatic. An observer watching you from a safe distance would see your spacecraft appear to slow, your movements becoming sluggish, your signals stretching out into longer and longer wavelengths. The light coming from you would redden. The signal would stretch. Eventually, you would appear to freeze, hovering just above the event horizon, dimming like an ember, fading over what would seem to the distant observer to be an eternity. You would never appear to cross. You would simply fade. But from your own perspective, something entirely different would happen. If the black hole is large enough, you might not feel anything unusual as you cross the event horizon. There's no wall there, no barrier, no moment of obvious drama. The event horizon is not a surface you could touch or land on. It's a mathematical boundary, a line drawn not in matter, but in the geometry of space-time itself. The point at which the escape velocity exceeds the speed of light. For a sufficiently massive black hole, the tidal forces at the event horizon are gentle enough that a person could cross without being torn apart. Not for small black holes. Those have enormous tidal gradients near the horizon. But for the supermassive black holes at the centers of galaxies, black holes billions of times more massive than our sun, the horizon can be so far from the center that gravity there is actually quite manageable. And so, you cross. The horizon passes over you like a shadow, and nothing changes except for one thing. Every path forward, every trajectory, every direction of motion now leads toward the center. Not toward a wall, not toward a point you can see or aim for, just inward, irreversibly, inexorably inward. In a black hole, falling toward the center isn't a direction in space, it's a direction in time. Let that drift through your mind for a moment. Inside the event horizon, the singularity, the center of the black hole, is not a place you can avoid by steering around it. It is your future. The way tomorrow is your future. The way you cannot stop time from moving forward, you cannot stop yourself from moving toward the center. In a sense, to be inside a black hole is to be inside a region where time itself points inward. Physicists describe this using the language of space-time diagrams, pictures where one axis is space and the other is time. Outside a black hole, your future points upward in time, and you can choose to move left or right in space. But inside the event horizon, something strange happens to the diagram. The directions rotate. What was the time direction outside becomes the space direction inside, and the space direction pointing toward the center becomes the time direction. Toward the center is no longer a place, it's a when. This is perhaps the most haunting aspect of the interior of a black hole. Once you're inside, you cannot hold still. Just as you cannot stop time from moving forward in your ordinary life, you cannot stop yourself from moving toward the singularity. It's not that something is pulling you. It's that the geometry of space-time itself leaves you no other direction to travel. As you fall, the world outside the event horizon becomes strange. The opening above you, the circle of the outside universe, begins to shrink. The light from all the stars in the cosmos concentrates into a narrowing ring above your head. It brightens, then fades, then closes. Eventually, there's no light at all from the outside world. Only darkness surrounds you, and ahead, the singularity waits. For a stellar mass black hole, those formed from individual stars, the fall from the event horizon to the singularity takes a fraction of a second. But for a supermassive black hole, one with billions of solar masses, the fall could take hours. Hours of falling through total darkness, through warped space-time, toward something we cannot fully describe. The singularity. This is where our mathematics gives out. This is where the equations of general relativity, the most precisely tested physical theory in history, simply fail to describe what happens. The singularity is the point where the equations predict infinite density, infinite curvature. matter compressed without limit into a region without dimension. And infinite is a word physicists distrust. When a theory predicts infinity, it usually means the theory is reaching the edge of its applicability. It means something else, something deeper, must take over. That something, most physicists believe, is quantum mechanics. Quantum mechanics is the language of the very small. It governs electrons and photons and quarks, the fundamental particles of matter. And at the singularity, matter is compressed to scales so tiny that quantum effects can no longer be ignored. But here's the problem. General relativity and quantum mechanics do not speak the same language. They have not been reconciled. The two greatest theories in physics, each astonishingly accurate in its own domain, contradict each other when pushed to extremes. The singularity is one of those extremes. Some physicists believe quantum gravity, the yet undiscovered theory that unites them, will replace the singularity with something real and finite, something with structure, something that doesn't become infinite. Perhaps the crushing compression is halted, not by any force, but by the fundamental graininess of space itself. Perhaps below the Planck length, the smallest possible unit of distance, space simply doesn't exist in the way we imagine. The singularity, in this view, is not a real place, but a symptom of an incomplete theory. Others have proposed even stranger possibilities. Some theories suggest that the interior of a black hole might connect to another region of spacetime entirely. A bridge through the geometry, what we sometimes call a wormhole. The mathematics of general relativity does permit such structures. They're called Einstein-Rosen bridges, named for Einstein and his collaborator Nathan Rosen, who noticed in 1935 that the equations describing a black hole contained a curious mirroring. If you look at the full mathematical solution, the space-time around a non-rotating black hole doesn't just contain one universe. It seems to imply two, connected at the singularity by a narrow tunnel through the geometry. But this bridge, if it exists, is not something you could survive or traverse. For a classical black hole, the Einstein-Rosen bridge closes faster than any signal could cross it, even at the speed of light. You would reach the singularity long before you could exit the other side. More exotic possibilities arise when you consider rotating black holes. And most real black holes do rotate. They are formed from rotating stars, and angular momentum is conserved as the star collapses. A rotating black hole is called a Kerr black hole, named after Roy Kerr, the New Zealand physicist who solved Einstein's equations for rotating mass in 1963. The solution revealed something remarkable. Around a rotating black hole, space itself is dragged along by the spin. Not just the mass of the black hole curving spacetime, but the rotation actively pulling spacetime around with it, like a spoon stirring honey. This region of dragged spacetime is called the ergosphere, and within it, nothing can remain stationary. Even light is swept along by the rotation. Within a Kerr black hole's interior, the mathematics becomes extraordinary. Instead of a single singularity, the equations suggest a ring singularity, a circle of infinite density, not a point. And the equations of general relativity hint that the interior of a rotating black hole might contain regions where time behaves in ways that defy ordinary intuition, where closed time-like curves might exist, loops in space-time where you could, in principle, encounter your own past. Most physicists believe these exotic structures do not survive in the real universe, that quantum effects or instabilities in the interior would destroy them before they could be traversed. But the mathematics leaves the door open, just a crack, and in that crack, the imagination of generations of physicists and dreamers has wandered. Let's wander there too, just for a moment. Not into the danger, into the wonder. Imagine that a black hole is not just an ending, but a kind of membrane. A place where the universe folds over on itself, where matter that falls in doesn't simply stop existing, but transforms, converts, becomes something else in some other region of the cosmos. Some theorists have speculated that every black hole might be the seed of a new universe, that the enormous energy compressed in a singularity might trigger a new Big Bang in some perpendicular dimension of spacetime, a universe utterly inaccessible from our own, born from our death, carrying forward some faint echo of the physics of its parent. This is speculation. Beautiful, honest, serious speculation, but speculation nonetheless. We have no way to test it, no way to look inside a black hole and see what becomes of the matter within. No signal can emerge from beyond the event horizon to tell us what waits there. And this brings us to one of the deepest puzzles surrounding black holes. A puzzle so profound, it has preoccupied physicists for half a century and remains unsolved. The information paradox. In 1974, the physicist Stephen Hawking made a discovery that shook the foundations of physics. He showed that black holes are not entirely black. At the quantum level, something extraordinary happens near the event horizon. Virtual particle pairs, which in quantum mechanics flicker in and out of existence everywhere all the time, can be separated by the event horizon. One particle falls inward, the other escapes outward. To a distant observer, this looks like radiation streaming from the black hole. Radiation carrying energy. We call it Hawking radiation. The consequences are staggering. If a black hole emits energy, it slowly loses mass. Over time, it shrinks. Over an almost incomprehensibly long time, it evaporates entirely. A black hole the mass of our sun would take longer than the current age of the universe to evaporate. A stellar mass black hole might take 10 to the power of 70 years. But eventually, according to Hawking's calculation, the black hole is simply gone. And here is the paradox. Everything that fell into the black hole, every piece of matter, every photon, every particle carrying with it the encoded information of what it was and where it came from. Where does that information go when the black hole evaporates? In quantum mechanics, information is sacred. It cannot be created or destroyed. The laws of quantum physics guarantee that information about the past is always recoverable in principle, even if the matter itself has changed form. But if a black hole swallows information and then evaporates, taking everything with it, that information seems to disappear permanently, violating the laws that govern the quantum world. This is the black hole information paradox. And it is not merely a technical puzzle. It goes to the heart of whether general relativity and quantum mechanics can ever be reconciled. Whether the universe is, at its deepest level, consistent. Hawking himself, for most of his career, believed information was truly lost. He thought black holes represented a genuine exception to the rule of information conservation, a permanent destruction of knowledge. But late in his life, he changed his mind. He became persuaded that information must escape, somehow, encoded in the faint correlations of Hawking radiation, not in a way that would allow you to decode what fell in without knowing everything about the radiation at every moment of the black hole's life, but present, somewhere, somehow, in the quantum whisper of the evaporating whole. The details of how this works remain deeply contested. One fascinating proposal involves the concept of the holographic principle. The holographic principle emerged from the work of physicists Jacob Bekenstein and Stephen Hawking in the 1970s. Bekenstein noticed something strange about black hole entropy, the measure of disorder associated with a system. He proposed that the entropy of a black hole is not proportional to its volume, as you might expect, but to its surface area, to the area of the event horizon. What this suggests is profound. The information content of everything inside a black hole is encoded on its surface, not within its volume, not in the three-dimensional interior, but on the two-dimensional boundary. If this is true for black holes, could it be true for the universe itself? Some physicists believe the answer is yes, that our three-dimensional universe might itself be a kind of holographic projection from a two-dimensional surface at its boundary, that everything you see, every star, every atom, every memory, might be encoded on some cosmic horizon that surrounds all of existence. This is the holographic principle, and while it sounds like science fiction, it has become one of the most actively developed ideas in theoretical physics over the past 30 years. Supported by deep connections between string theory, quantum gravity, and thermodynamics, it suggests that what happens inside a black hole might not be lost at all, that it persists, encoded on the surface, carried away in the radiation, preserved in the subtle quantum correlations of Hawking's slow thermal glow. Whether this is truly the answer remains to be seen, but the idea changes how we think about what a black hole is. Not just a region of no return, but a kind of cosmic archive, an extreme library where the story of everything that fell in is written in a language of quantum information on the very surface that marks the point of no return. Let's drift now toward the very largest black holes, the ones that sit at the centers of galaxies. These are called supermassive black holes, and they're genuinely hard to comprehend in scale. The black hole at the center of our own Milky Way, known as Sagittarius A*, has a mass 4 million times that of the Sun. Yet it occupies a space smaller than the orbit of Mercury around our Sun. The one at the center of M87, the galaxy whose shadow was first photographed in 2019, is 6.5 billion times the mass of the Sun. A black hole with a mass of 6.5 billion suns compressed into a region smaller than our solar system. And yet, despite this enormity, for a traveler falling into such a beast, the experience at the horizon would be startlingly calm. The tidal forces, the difference in gravitational pull between your head and your feet, would be gentle enough to survive. You could cross without knowing, without feeling, without even a dramatic sensation. The event horizon of a supermassive black hole might pass over you like a cloud moving over the sun, a shadow without weight. Only later, as you fell deeper toward the center over hours of plummeting through featureless dark, would the tidal forces eventually build, stretch, pull. the gradient of gravity growing inexorably stronger as you approach the center. Eventually, in the very final moments, the forces would become powerful enough to stretch matter apart, a process physicists have given the wonderfully evocative name spaghettification. You would be pulled into a long, thin stream, drawn into the singularity not as a body, but as a thread of atoms. But we are far from the singularity yet. We still have so much to explore on the way down. One of the strangest aspects of falling into a black hole is what you would see as you descended. Inside the event horizon, light from the outside universe can still reach you for a time, but it comes from a narrowing window above, and it comes distorted because you are falling so quickly, and because the geometry of space-time around you is warping dramatically. The light from the outside universe becomes compressed, blue shifted, arriving faster and faster, more and more energetically as you fall. In the final moments, the radiation from the entire future history of the universe outside might arrive all at once, compressed into a burst of high-energy radiation. This is called the blue shift singularity, and it's a feature of the mathematics of black hole interiors that is still being studied. Some physicists believe that this wall of radiation inside the event horizon, created by the blue shifting of Hawking radiation from the outside, might be so intense that it constitutes its own kind of barrier. A firewall. The firewall paradox, proposed in 2012 by Ahmed Al-Mehri, Donald Marolf, Joseph Polchinski, and James Sully, suggests that if information is truly preserved in Hawking radiation, then the inside of a black hole cannot be the smooth, quiet region that general relativity predicts. Instead, the event horizon might itself be a place of tremendous energy, a wall of fire that would destroy anything crossing it. This would mean the classic picture of a peaceful horizon crossing is wrong. That in reality, the moment you cross the event horizon of even a supermassive black hole, you would be instantly incinerated. The firewall paradox set off one of the most heated debates in theoretical physics in decades. It exposed a deep tension between quantum mechanics, general relativity, and the principle that observers falling through a horizon should not notice anything unusual. Three principles that cannot all be simultaneously true, if the mathematics is to be believed. The resolution remains elusive. Some physicists think the firewall is real. Others believe it dissolves when you account for the full quantum description of the spacetime. Still, others have proposed radical modifications to our understanding of spacetime itself, including the suggestion that the interior of a black hole might not actually exist as a separate region, but is somehow encoded in the exterior in a way that makes the question of what happens inside meaningless at the fundamental level. These ideas pull at the deepest threads of our understanding of reality. They suggest that space and time, the stage on which everything happens, may themselves be emergent, may arise from something more fundamental, something like quantum entanglement. In recent years, physicists have discovered a remarkable connection. The entanglement between particles on either side of an event horizon seems to be related to the very geometry of the spacetime connecting them. Cut the entanglement, and the spacetime disconnects. Increase the entanglement, and you effectively create a wormhole, a geometric connection through spacetime. This idea, developed in part by Juan Maldacena and Leonard Susskind, suggests that the connection between two entangled particles is not just a quantum curiosity, but a geometric fact. That entanglement and spacetime are two descriptions of the same underlying reality. If this is true, then the interior of a black hole might be connected to the exterior in a way that is deeply quantum, not through matter, not through light, but through the entanglement structure of the quantum fields that surround and pervade the black hole. The interior might, in some precise mathematical sense, be the exterior, seen from a different perspective. This is the frontier of physics, the edge of what is known. Beyond this, there is only the night and the quiet hum of questions that may take generations to answer. Let's drift for a moment away from the theoretical and return to what has been observed, to what the universe has actually shown us. Because we have now seen the aftermath of black hole collisions, not through light, but through gravity itself. In September of 2015, a signal arrived at 2 detectors in the United States. Each detector is an instrument called a laser interferometer, a device that uses laser light to measure the distance between mirrors separated by several kilometers with a precision that defies comprehension. These detectors can measure changes in distance smaller than 1/10,000th the width of a proton. The signal that arrived that September had traveled more than 1 billion light years. It was produced by 2 black holes, each about 30 times the mass of the Sun, spiraling together over millions of years and finally merging in a fraction of a second. In that final instant, the 2 became one, and the collision released more energy than all the stars in the observable universe combined. Not in light, in gravitational waves, ripples in the fabric of space-time itself. Those ripples traveled outward in all directions at the speed of light, crossing 1 billion light years of space, expanding and weakening as they went. And when they finally reached Earth, they had shrunk to an almost incomprehensible thinness. They stretched and squeezed the distance between the detector mirrors by about 1/10,000th the width of a proton. The detectors felt them anyway. This was the first direct detection of gravitational waves, a triumph of engineering, of persistence, of scientific imagination, a moment that confirmed one more extraordinary prediction of general relativity and opened an entirely new way of listening to the universe. Since then, we've detected dozens of black hole mergers, each one a collision of invisible giants, separated by unimaginable distances, singing to us in the language of gravity. Each signal a brief chirp, a rise and fall of space-time curvature, carrying information about the masses, the spins, the final moments of objects that can never be seen. Black holes are not just dark. They are the universe's most powerful speakers. Their mergers are the loudest events in the cosmos, heard not with ears, but with the sensitive machinery of human ingenuity, trained patiently on the curvature of space. And now, let's return to something quieter, something that happens over the longest time scales in the universe, the slow death of a black hole. We spoke of Hawking radiation, the faint thermal glow that a black hole produces due to quantum effects near the event horizon. For most black holes, this radiation is so weak as to be completely undetectable. The temperature of the radiation from a black hole, the mass of the Sun, would be less than 1/1000th of a degree above absolute zero. Far colder than the cosmic microwave background, the ambient temperature of the universe. Such a black hole is actually absorbing more radiation from the universe around it than it emits. It is, in a sense, growing slowly, despite Hawking radiation. Only when the universe cools sufficiently over unimaginable future epochs would such black holes begin to truly evaporate. And then the process would be almost unfathomably slow. A stellar mass black hole might take 10 to the power of 70 years to evaporate completely. A supermassive black hole, 10 to the power of 90 years or more. These timescales are meaningless by ordinary reckoning. The current age of the universe is about 14 billion years. 100 trillion years from now, the last stars will have burned out. The galaxies will be dark. 10 to the power of 30 years from now, even the cold remnants of dead stars may have decayed. And still, the black holes would persist, patient, silent, slowly shrinking. The last objects of consequence in a cooling, darkening cosmos. In the very final moments of a black hole's life, the evaporation accelerates. As the black hole shrinks, its temperature rises. As its temperature rises, it radiates more intensely. The process becomes a feedback loop, faster and hotter and brighter until in the last fraction of a second, the remaining mass of the black hole, perhaps a few thousand tons compressed into the smallest possible volume, evaporates in a burst of radiation. A final flash, a bright punctuation at the end of an almost infinite story. No such event has ever been observed. The universe is too young. But in principle, somewhere in the far future, a universe full of slowly cooling black holes will witness these tiny, brilliant deaths, the last fireworks of the cosmos, each one a mystery concluding itself in light. And what is that burst? What is in that final radiation? That, physicists believe, is where the information must finally emerge. All the history of everything that ever fell in, encoded somehow in the correlations of the last flash of light. The library of the black hole, finally opened. Whether that information could ever be decoded by any observer, any intelligence, is another question. Almost certainly not in any practical sense. But its presence there, its preservation in the quantum correlations of Hawking radiation, would mean the universe has kept its promise, that nothing is truly lost, that even in the darkest place, the longest silence, the most extreme compression, the universe remembers. There's something quietly beautiful about that, something almost like comfort in the idea that the universe is not careless with its contents, that every particle, every photon, every moment of existence is preserved somewhere in the geometry of reality, even if it can never be read again. Let's drift now to something perhaps surprising: the smallest black holes, and the ones we may not yet fully recognize. The large black holes we've discussed are formed from the collapse of massive stars, or from the mergers of smaller black holes over cosmic time. But some physicists have proposed that black holes could also have formed in the very earliest moments of the universe. In the first fraction of a second after the Big Bang, when the universe was so hot and dense that quantum fluctuations in energy density could have been large enough to trigger gravitational collapse. These are called primordial black holes, and if they exist, they could be very small indeed, smaller than a proton, or they could be large, having had the entire age of the universe to accumulate mass. Some researchers have proposed that primordial black holes might make up a fraction of the dark matter. that mysterious, invisible component of the universe which holds galaxies together but has never been directly detected. We don't yet know if primordial black holes exist. No confirmed detection has been made, but the search for them is actively underway through gravitational micro-lensing surveys, through the search for anomalous patterns in gravitational wave observations, through careful analysis of the cosmic microwave background. If primordial black holes are ever discovered, they would rewrite the history of the early universe. They would tell us about conditions in the first instance after the Big Bang, a window into a time no telescope can reach. And there are smaller possibilities still. Some theories of particle physics predict that tiny black holes might be created in particle accelerators. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, has been producing collisions with enough energy that some versions of extra dimension theories suggest microscopic black holes could form. They would evaporate almost instantly through Hawking radiation, leaving distinctive signatures in the detectors. So far, no such signatures have been found. But the search continues, and the possibility remains open. A black hole the size of a quantum particle, created, lived, and extinguished in less time than it takes a single nerve impulse to cross a synapse. What an astonishing range of scales this single phenomenon inhabits, from quantum specks to objects billions of times the mass of the sun. From the first fraction of a second after time began to the last moments of a cooling cosmos. Black holes are present across almost the full range of space and time that the universe contains. Now let's think for a moment about something closer to us, something personal. Every atom in your body has a history. The hydrogen atoms were forged in the Big Bang itself, 14 billion years ago. The carbon, the oxygen, the nitrogen, the iron in your blood, all were forged in stars. Many of those stars may have ended their lives as black holes. The iron in your blood was forged in the heart of a massive star that burned for millions of years and then exploded as a supernova. The remains of that star may be a neutron star, spinning rapidly somewhere in the galaxy, pulsing out radiation in precisely timed beams. Or it may have collapsed further. It may be a black hole. In a very real sense, the atoms that make up your body have brushed the edge of a black hole's birth. They were scattered by the explosion that could have formed one. They carry within them the legacy of stellar extremity. We are not separate from these objects. We are downstream of them, made from their violence and their grace, their burning and their dying, their final compression and their explosive dispersal. When you look at a night sky and try to find a black hole, you won't see one. You'll see the stars that will become them. You'll see the light of galaxies whose centers harbor supermassive ones. You'll see, if you know where to look, the faint evidence of the bending of starlight around regions of extreme gravity. The universe is full of these objects, and they have been part of its story since almost the very beginning. There is something in the contemplation of a black hole that pushes us right to the edge of language, the event horizon, the region beyond which we can never know, the singularity, the place where knowing itself seems to break down, the information paradox, the question of whether anything is truly preserved or lost. These are not just physics problems. They are philosophical ones. They touch on the nature of knowledge itself. on whether the universe has a consistent underlying logic, on whether reality is something that can be fully described, or whether there are regions of it that will always be hidden from us. There's a version of the black hole as a metaphor for the limits of inquiry, as a reminder that the universe does not owe us complete transparency, that there may be truths which are real and which matter, and which nevertheless lie beyond the horizon of what can ever be measured or known. And there is something comforting in that, if you let yourself sit with it. The idea that mystery is not a failure of understanding, but a feature of reality, that the universe is larger than our instruments, more complex than our equations, more patient than our curiosity. We began tonight with a dying star, a star massive enough, heavy enough, that when its fuel ran out, there was no force in nature sufficient to hold it up against its own gravity. And so it fell into itself, into a new kind of existence, defined not by what it is, but by what it prevents, by the absence of escape, by the permanent closing of a door. And in that closure, all of physics becomes strange. Time itself bends toward the center. Space warps beyond recognition. Matter compresses past the limit where our equations can follow. And somewhere in that compression, in that utter extremity, something happens that we cannot yet describe. Perhaps a new universe opens. Perhaps information is preserved in ways we cannot yet read. Perhaps the laws of physics, which have been so reliable up to the horizon, give way to something deeper, something that unifies the very large and the very small in a theory we have not yet found. What we know for certain is this: black holes are real. We have seen their shadows. We have heard their mergers. We have measured the orbits of stars around the invisible mass at the center of our own galaxy. We have confirmed their existence through dozens of independent lines of evidence. They are not theoretical curiosities or mathematical fictions. They are the most extreme objects the universe produces. And they are out there in their billions, silent and dark and patient, pulling everything that wanders close enough into their long, slow embrace. And as you lie here now, with the day behind you and the night all around, you can let the image of a black hole settle gently at the edge of your thoughts. Not as something frightening, not as a place of danger or loss, but as one of the universe's most honest expressions of its own strangeness. A place where the rules run out, where the known becomes unknown, where the edge of knowledge sits right next to the edge of everything. You are made of atoms that have known the outskirts of such things. You carry in your body the record of stars that burned bright enough to end this way. And you are here, in the warmth of a world that keeps its gravity gentle enough, its light generous enough, to let life persist and wonder and rest. The universe has been building toward moments like this one for 14 billion years. Stars burning and dying, galaxies assembling, elements scattered across space, life arising, and somewhere in that long unfolding, a creature that can lie down at the end of a day and think about black holes, about the shape of time, about what it means that there are places beyond which nothing returns. That creature is you. And you don't need to understand it all tonight. You don't need to hold all the paradoxes together. You can simply let them drift, like stars reflected on still water, beautiful and present and not requiring anything from you. The event horizon holds its secrets. The singularity keeps its silence. The Hawking radiation whispers in frequencies too faint to hear, and you, quietly breathing, are resting on a small blue world that moves through a galaxy that turns around a black hole 4 million times the mass of the sun, and everything continues. If you happen to still be awake, you can go ahead and watch the next chapter now. And if these quiet journeys through science give you a peaceful way to end your day, consider liking and subscribing to the channel. It helps other curious, sleepy souls find their way here too. I hope you sleep well and dream softly. Good night.